Welcome back, my dear students. Last class we had discussed the different types of joints used in a bolted connection like lap joint, single cover butt joint, double cover butt joint. So today's class we will start with some certain terminologies used in the design of bolted connections. As you can see in clause number 10.2.4.1. So here I'll draw a single covered butt joint. I'll draw a single cover butt joint. So this is a single cover butt joint. Now I'm applying a force. I'm applying a force P. I'm applying a force P in this direction, a tensile force P in this direction. Then the distance between two fasteners, the distance between two consecutive balls measured parallel to the direction of the force is called as pitch, denoted by small p. So this distance is denoted by small p. This small p is called as pitch. Now the distance measured perpendicular to the two consecutive balls is called as gauge distance, denoted by small g. This is g, denoted by small g. G is gauge distance. Gauge distance. Now the distance between the center of end bolt and edge of the plate element measured parallel to the direction of the force is called as end distance. That is, I could say this is parallel to the plate. This is called as end distance, and the distance between center of the end bolt and edge of the plate element measured perpendicular to the direction of the force is called as edge distance. That is, this distance I could take it as edge distance. This is called as edge distance. So these distances what I have said now all are taken from the center line of one bolt to the center line of other bolt or edge or end of the plate. So I could say here the pitch is the distance measured between two consecutive bolts measured parallel to the direction of the force. You can see here the gauge distance, it is the distance between two consecutive bolts measured perpendicular to the direction of the force. The end distance between center of the end bolt and edge of the plate element measured parallel to the direction of the force. And edge distance, it is the distance between center of the end bolt and edge of the plate element measured perpendicular to the direction of the force. For understanding purpose, for understanding this, I will tell an easy method. That is, you can club gauge and edge together. Both are taken. There is a pronunciation for G there, edge gauge. So you can take it, and always gauge is perpendicular to the direction of the force. Similarly, edge is also perpendicular direction of the force. So pitch and end will be together, gauge and edge will be together. As you can see here, the edge and the end distance 10.2.4. The edge distance is the distance at right angles to the distance at right angles to the direction of stresses from the center of a hole to the adjacent edge. The end distance is the distance in direction of the stresses from the center of the hole to the end of the element. So I hope it is clear for you. You can see in clause number 10.2.4. I'm having a plate like this, and the bolting arrangement I'm making it like this. I have one bolt here, I have another bolt here, I have another bolt here, I have another bolt here, another bolt here, and another bolt here. Then parallel to the direction of the force, if two consecutive bolts are not in the same line, then it is called as a staggered bolting. That is, parallel to the direction of the force. If I am applying the force like this, parallel to the direction of the force, if two consecutive bolts are not in the same line, if the two consecutive bolts are not in the same line, here the line is here, that direction, then it is called as staggered bolting, and the distance between two consecutive bolt, this distance between two consecutive bolt, this distance between two consecutive bolt is called as staggered pitch. It's called as staggered pitch, denoted by small s. And as we had discussed before, the pitch means distance between two consecutive bolts in the direction of the force. So this is pitch. This is pitch and this is staggered bolting. Hope you have understood this. So now we are going to discuss the failure of bolted joints. The failure of bolted joints. So the failure of bolted joints is mainly due to failure of bolt or failure of plates. Failure of bolt or failure of plates. So we will discuss this in detail. What is the failure taking place here? The first one is failure of bolt. In failure of bolt, there are two types of failure. First one is shear failure of bolt. Second one is bearing failure of bolt. Shear failure of bolt and bearing failure of bolt. First, we will see the shear failure of bolt. What do you mean by shear failure of bolt? Consider I am applying a force like this, a force in this direction, a force in this direction, and another force in this direction. So what happens is this bolt has a tendency to cut into two pieces from these positions, right? Either from here or from here, this position or this position. That is, the bolt will, see here, the bolt will get cut into two pieces like this. That is, here the bolt will get cut like this, and this failure of bolted connection is called as shear failure of bolt. This type of bolt failure in bolted connection is called as shear failure of bolt. You could see here, if there is only one cut that is happening here, there is only one plane which gets cut into two pieces, then this is called as single shear. So in case of lap joint, single cover butt joint, there occurs single shear. But when we are connecting a double cover butt joint, there can occur a failure at this plane as well as at this plane, at this plane. At these two planes, the failure can take place, and only after these two planes get cut, the failure of the plate or the element will take place. Such type of failure in bolted connection is called as double shear failure, and this happens in case of double cover butt joint. This happens in case of double cover butt joint. Now we will see the second kind of failure in bolted connection, that is the bearing failure of bolted joints. In bearing failure of bolted joints, I am going to apply the same load as we have shown before. So when I apply the load like this, what happens here is the bolt changes its shape from circular to elliptical. See here, the shape of the bolt here has changed, or the shape of the bolt hole here has changed. So the bearing failure of the bolted joint take place like this. That is, it changes its shape from circular to elliptical. It changes from circular to elliptical. Then such kind of failure is called as bearing failure of bolted joints. Now these are the two types of failure taking place in case of a bolted joint, that is shear failure of bolt and bearing failure of bolt. Hope you are clear on this. Now we will move on to the second kind of failure for a bolted connection, that is your failure of plates. In failure of plate, you can see the first one, that is shear failure of plates. That is, suppose I am having a lap joint, there is only one bolt. So I'm applying a force like this, I'm applying a P force like this, then at section 1 if I'm considering this as section 1 if I'm considering this as section 1 and I'm considering this as section 2 This is section 2.2. Then at section 1.1 cracks are developed due to tensile stress. At section 1.1 the cracks are developed due to tensile stress, and at section 2.2 the failure or the cracks are developed due to shear stress, or the failure due to the shear stress take place, right? The cracks are developed due to shear stress. So such a failure that occurs in the plate is called as shear failure of plate. The second failure that takes place for the plate is splitting failure of plate. As you can see in the picture, the plate splits into two parts over here. The plate splits into two parts over here, and this type of failure is called as splitting failure of plates. It occurs due to the diagonal tension in the plate at the bolt level. It occurs due to the diagonal tension. In the plate at the bolt level. That is splitting failure of plate. Now the third one is bearing failure of plate. That is, suppose I'm having a lap joint like this. So when I'm applying the force, I'm applying the P force like this. What happens is the plate will yield in this way, and the shape of the plate gets distorted. And this type of failure is called as bearing failure of plate. The next one is tearing failure or tension failure of plate. So what happens here is when I'm applying a force P, along the line of the bolt. The plate will get teared into two parts due to the tensile stress. The plate will get teared into two parts at the weakest point, that is along the line of your bolt. The net area, I will discuss that later, the net area will be very much less. As a result, the plate will get teared into two parts along this position, and this type of failure is called as tearing failure or tension failure of plates. So I could summarize it. The failure of bolted joints are due to failure of bolt and failure of plates. In failure of bolt, there are shear failure of bolt and bearing failure of bolt. In failure of plate, there is shear failure of plate, splitting failure of plate, bearing failure of plate, and tension failure or tearing failure of plate. Out of this, the shear failure of plate, the splitting failure of plate, and the bearing failure of plate can be avoided if we provide sufficient end distance. That is, by providing proper end distance, we can prevent these three failures. So in design of a bolted joint, we have to consider the remaining three failures. That is shear failure of bolted joints, bearing failure of bolt, and tension failure of bolt. So out of these three, the least value will be the capacity of the joint. That is, when it reaches the maximum of any of these three, the failure of the joint will take place. That is, all these three, that is the shear failure of plate, splitting failure of plate, and bearing failure of plate, can be avoided by providing end or edge distance. And the remaining three, that is shear failure of bolt, bearing failure of bolt, and tensile failure of plate, we should design. Now consider this as a part of a structure. Where there are many joints, and this portion is actually called as a gusset plate. You will study that later, which means the connection is taking place through this plate. As an engineer, we have to ensure that the shearing strength and bearing strength of bolt is always greater than the tensile strength of the plate. This is because the connection failure is more dangerous than component failure. That is, if suppose this particular component fails, it's okay, we could manage with the other four components. But suppose this connection fails, what happens? This component, and all will fail. So that we need to make sure that the shearing strength and bearing strength of the bolt is always greater than the tensile strength of the plate. So summarizing it, I could write the strength of a bolted joint is taken as the least value of the shear strength of the bolt or the bearing strength of the bolt or the tensile strength of the plate. So we will discuss these three separately. The first one is the shear strength of the bolt. The shear strength of the bolt is explained in clause number 10.3.3. It is explained in clause number 10.3.3. You could see here in 10.3.3, page number 75, it is written the shear capacity of the bolt. The shear capacity of the bolt. The design shear strength of the bolt VDSB shear strength is given by VDSB is equal to, it is given as VDSB is equal to VNSB divided by gamma MB. VNSB divided by gamma MB, where VNSB is equal to, where VNSB is the nominal shear capacity of the bolt given by Fu divided by root 3 into NNANB plus NSASB, where Fu is the ultimate tensile strength of a bolt, Nn is the number of shear planes with threads intercepting the shear plane, Ns is the number of shear planes without threads intercepting the shear plane, ANB is the nominal plane shank area of the bolt, and ASB is the nominal plane shank area of the bolt, and ANB is the net shear area of the bolt at the threads. Net shear area at the threads. We will discuss this in detail when we are going for some numericals. You will understand more clearly when we are going for numericals. And this gamma MB value, we'll get it from table number 5 of IS 800 2000. So this gamma MB value, you could see here, table number 5 of IS 800 2007. You'll get this from the table number 5. Now the next is the bearing strength of the bolt. It is given in 10.3.4, page number 76. You could see here the bearing capacity of bolted joint. Bearing capacity of the bolted joint. That is the design bearing strength of a bolt on any plate VDPB as governed by the bearing is given by VDPB is equal to VNPB divided by gamma MB. This gamma MB you'll get it from table number 5. And VNPB is again that is the nominal bearing strength of the bolt is given by 2.5 kb dtfu, where kb is the smaller of E by 3 d naught or P by 3 d naught minus 0.25 or FUB divided by FU or 1. So smaller of these four values is your kb, where E and P are the end and pitch distance of the fastener respectively. D naught is the diameter of the hole. FUB and FU is the ultimate tensile stress of the bolt and the ultimate tensile stress of the plate respectively. D is the nominal diameter of the bolt and T is the summation of the thickness of the connected plate. So this also you will get more clear when you are doing the numericals. The third failure or the third strength determining factor is the tension capacity of plate. So this is given in clause number 6.3, that is the design strength due to rupture of critical section is given by TDN is equal to 0.9 ANFU divided by gamma ml. That is, you will get TDN, that is the design strength in tension of a plate. TDN is equal to 0.9 ANFU divided by gamma ml. This gamma ml value also you'll get it from table number 5. AN is the net effective area of the member. You don't need to take the equation, I'll tell you how to do it. And Fu is the ultimate stress of the material. And you need to understand the clause number 6.2, that is the design strength due to yielding of the cross section. That is, the plate can either, I'll take it like this. Suppose I'm having a section like this. I'm having a lap joint like this. So while applying the force, sometimes the failure can occur like this, that is the net section rupture can take place, or sometimes the plate can yield like this, and the bearing failure, that is gross yielding of the section takes place. So either or this can occur or this can occur, both we will consider as the failure of the plate, so when the net section rupture occur, it is TDN 0.9 Fe divided by gamma ml, and when the whole solid plate yields, then it is called as TDG, that is the gross yielding of the plate, which is given by AgFy divided by gamma m naught, where Ag is the gross area of the cross section, Fy is the yield stress of the material, and m naught is the partial safety factor for failure in tension by yielding. So these three are the strength of a bolted joint, that is least of these three: shear strength of the bolt, bearing strength of the bolt, and tensile strength of the plate will give you the strength of a bolted joint. The efficiency of a bolted joint is given by, we are denoting this efficiency as eta. If entire width or full width of the plate is given, then efficiency in percentage is equal to least value of VDSB or VDPB or TDN divided by strength of the solid plate into 100. Now, if the total width of the plate is not provided, we will take per gauge length. That is, efficiency of the bolted joint will take per gauge length. Then, for gauge length, the efficiency is given as least value of VDSB or VDPB or TDN per gauge length divided by strength of the solid plate per gauge length into 100. So if you are asked to calculate the efficiency of the bolted joint for entire width of the plate, it is least value of the shear strength or bearing strength or net tensile strength of the plate divided by solid strength of the plate into 100. If the entire width is not given, we will go for per gauge length, or the same thing what I said before. So today's class we will end up with here. For the next class onwards, we will start the numericals. There you will get more idea of what we have studied.